What we're going to do today is we're going to have a bit of a lecture, which will be basically introducing you to what is earth sciences, which will include some background on plate tectonics, which you might have heard of, and geological time. So some of this will be based on research that I've done and is done in the department in Edinburgh here. And then we're going to have a short practical session, depending on how much time we've got, to basically show you some of the things that we might do in a practical in university. And also some of the basically what maybe a geologist might use in terms of the skills when we're making observations of geological samples. First of all, so I thought I'd just start off with something that you might be more familiar with. So this is a Wordle of the Wikipedia entry for geography. So this basically describes all of the buzzwords that come up when you do an internet search for geography. And if you just look at these are basically describing what geography is. And if you just looking at the environment around us and how humans interact with that environment. Okay, so things like mapping out distributions of people, understanding processes that happen on the surface of the Earth. But you can see that one of the key words that comes out of this is really understanding the Earth. Okay, and this is what earth sciences is. So if we just go look at the Wordle for earth sciences, so what earth sciences is really aimed at focusing on is the physical environment of the Earth. Okay, so looking at the atmosphere, looking at the oceans, looking at the solid Earth, so the rocks, the soil, everything all the way down to the core, the centre of the Earth, to really understand the physics, the chemistry, and the biology of this really complex interacting system. Okay, so quite a lot of the time, earth sciences gets conflated with the geology, and this was basically a rebranding exercise that was done about 20 years ago when a bunch of geology departments decided to start calling themselves earth sciences departments, because they started to broaden out from this kind of somewhat more narrow view of just looking at rocks to try and look at the system of the Earth as a whole. Okay, so incorporating the atmosphere, oceans, the biology. Okay, but quite a lot of the stuff that earth sciences encompasses is what would we traditionally think of as geology, and we'll be looking at some of this in the fields tomorrow. We've got some samples of this, right? So we're really looking at the solid Earth, its history, the processes that have shaped its history, and the processes that determine what's going on the Earth's surface now. And just as an aside as well, it's not so much an aside, but it's not, geology isn't just an optical kind of observational science. We don't just look at stuff. We also use a bunch of other sciences to help us understand how the Earth works. So this is, for example, this is geophysics. So geophysics uses a bunch of physical techniques. So it uses electromagnetic waves, uses seismic waves to understand what's going on inside the Earth. But it also uses the concepts of physics, okay, so things like the conservation of mass, momentum, to model how the Earth works. Okay, so geophysics basically looks two ways. It uses physics to look at the Earth, and then it uses physics to kind of model how the Earth works. Okay, so earth sciences at university. So I put these two slides up, two pictures up, really to stress the importance of earth sciences, of basically geologists, to the Earth around us. So this is a lecture theatre. This is just obviously a stock photo from the University of Edinburgh's kind of publicity department. You can see it's a nice full lecture theatre with a bearded old white guy giving a nice lecture that everyone is paying attention to, which almost never happens. But if you look around that room, in fact, if you look around this room, everything in that room, okay, the floor, the chairs, the light fittings, the bench, the computers, everything in that room, okay, was dug out of the ground by a geologist. Okay, all of the raw materials to produce everything in that room has been produced by a geologist, except all the stuff that's made of wood, okay, or some of the natural fibres. They were grown by plants, and those plants need nutrients, nitrate, phosphate, potassium, micronutrients like iron. So understanding those nutrient cycles is also a critical part of earth sciences. Okay, so without earth sciences, none of this fantastic stuff would be possible. Okay. Also put these up because these show some very nice, well-lit, warm, comfortable lecture theatres. So all of that energy that is being produced to power this fantastically interesting lecture is reliant on earth sciences. Now, in the past, that has largely been us digging oil and gas out of the ground, which has not turned out to be such a fantastic idea in hindsight. Even so, for instance, in Scotland, there are some days where we get over 100% of our electricity from wind power, which is great. But those wind turbines, they need raw materials that come out of the ground by geologists. They need installing, okay, which needs ground investigations to make sure that they're put in the right place. Okay, they need environmental impact assessments on the peat bogs that they're installed on, or in the marine environment. So all of these problems to do with energy require earth scientists to sort them out. So it's kind of like this transitioning of our energy kind of universe from an oil and gas and coal dominated to a kind of renewables dominated is actually a really exciting time to be an earth scientist, because there are all of these interesting problems and challenges that are being brought up. So earth scientists basically look at the earth. Okay, so we look at the earth, but we don't just look at it kind of, so these top images up here. So this is a kind of a false color image of the earth with the ocean stripped away. This is just a satellite image of the earth. We don't just look at it kind of with our eyes. We also use things like remote sensing to determine. So this is a remote sensing image of Venus. So we also look at other planets, looking at how the topography is. We map out things like the different types of rocks we find. So this is a geological map of the Earth. We look inside the Earth here. So this is a cutaway model looking at the different layers we find down inside the Earth. So we've got a solid iron core in the middle of the Earth, surrounded by liquid metal. Then we've got a solid-ish rocky mantle, and then this very thin layer on the outside is the rocky crust that we live on. Okay, so we images like this are produced by our understanding of geophysics of the Earth. This is a map of, so the Earth is not completely spherical. So this is a map of the gravitational equipotential surface of the Earth. So you think basically if the Earth was a perfect sphere with uniform density, gravity would be the same all the way around the Earth, but in fact it is not, because different parts of the Earth kind of like bulge out. We have deep ocean trenches and mountains, and they basically cause this equipotential gravitational surface to be kind of like all lumpy. And we can measure that with satellites, and that tells us, those measurements tell us something about the structures and the processes that are going on deep in the Earth to drive and cause these things like mountains in the Himalayas, or maybe in the African Rift there. Okay? So we're basically trying to look at the Earth in a whole bunch of different ways. Okay, so I mentioned oil and gas earlier, so this is really a slide to show one of basically the biggest challenge global society has over the next, I guess, the next 50, 100 years. So the map is a map of the temperature difference between the average annual temperature for each kind of like place on the Earth last year relative to 100 years ago. So the average between 1900 and 1930, so around 1915. Okay. The grey areas are where we have no data. So that's not because we have no data now, it's because we had no data in 1915. And you can see that almost everywhere on the Earth is a lot warmer than it was 100 years ago. Okay, and that warmth is not uniformly distributed around the Earth, so that's something that we have to understand, which regions will cool faster, will warm up faster and become more heavily impacted. So you can see the high northern latitudes, so Russia, Canadian Arctic, are warming much, much faster than the tropics, but the tropics are nonetheless still warming pretty dramatically. And this warmth is caused by our anthropogenic emissions of CO2. Okay, so this is over on this side we've got a graph of the carbon dioxide concentration in the atmosphere. So this is 400,000 years ago. So that's a very long time ago. So humans were kind of like, migrating out of Africa around this kind of time. And you can see that we've been through a bunch of cycles of climatic change where carbon dioxide concentrations have gone up and down kind of naturally over this range of maybe 300, 200 parts per million. So still really low concentrations, but substantial variations. But this kind of bit on the end here, this increasing up, we're now over 400 parts per million. That's a massive perturbation compared to what we've had going on in the past. Okay? And even these perturbations that were natural do have or have had huge climatic influences. And some of you will see that in one of the practicals on tomorrow and Wednesday. Oh, Robin. So this is what's going to happen. It ain't pretty. So over on the far left, you guys, this is looking forwards into the future. So these are basically with climate models. So this is 100 years ago, this is now, this is now, this is 100 years in the future, and this is 200 years, 300 years in the future. And you can see that the different coloured lines kind of increase with temperature through time. Okay, and the different coloured lines are basically different emission scenarios. They're basically different choices that we can make as a society. So the red line is we carry on burning fossil fuels like they're going out of fashion. And the blue line is we kind of do everything we possibly can to stop burning fossil fuels. So some of you might have heard of this 2 degree temperature target that we want to stay below. So you just point out that the axis on this 0 is arbitrarily pinned somewhere around 1990. And the actual 0 for the 2 degrees target is kind of the pre-industrial value. So 2 degrees warming is actually here, okay, at about, well, actually looking at 1.5 degrees on this axis. So if we want to stay below 2 degrees warmer, we have to choose the blue curve, basically. It's very unlikely that if we choose to follow the green curve, then we will achieve that target. It will be bad. It will be bad anyway. So these are what these curves mean in terms of emission scenarios. So the red, the blue, and the green, and there's another yellow option on here as well. Moving forwards over the next 100 years, this is what our emissions would have to look like for these temperatures to happen. Okay, so you can see if we follow the red curve, we carry on with very, very high emissions, okay, and that leads to very high temperatures. Whereas in the blue one, we have to, for us to keep below 2 degrees Celsius increased warming, we have to drastically reduce our emissions over the next kind of few decades. And at the later half of this century, we have to have 0 or below emissions. So we have to have negative emissions. So that's not just not burning fossil fuels anymore, that's actively taking carbon dioxide out of the atmosphere and putting it in the ground. Okay? So this is a monstrously huge logistical challenge, okay, which only geologists can fix, okay, because only geologists can achieve negative emissions, because that involves putting stuff into the ground, okay, and that's a geological or an earth sciences problem. It's a little bit worse than this as well, because even this proposed scenario over here, where we stop burning fossil fuels and we start doing carbon capture and storage and taking carbon dioxide out of the air, putting it in the ground, if we actually look at what this emission scenario actually entails, so this graph over here on the right, these are basically what we expect our world economy to be doing for each of these different colours. So this is what we're doing now, this is the blue line, this is the green line, this is I think the yellow line, and this is the red line. Okay, so so the black bars are us burning coal, the blue and the orange are us burning different fossil fuels, natural gas and oil. So even with this scenario, okay, the forecast is from kind of economists that the world economy will not be able to stop burning fossil fuels by this point here, which means that we must have huge amounts of carbon capture and storage of those fossil fuels and from the air into the ground for this to become a reality. Okay? So I don't mean to be terribly downbeat about it, but this is very unlikely to happen. Okay, but if it is going to happen, and it kind of does need to happen for us to kind of have a nice safe planet, we need Earth scientists to figure out ways of safely putting that carbon dioxide in the ground. Okay, so these are, so if we just look over on the left-hand side here, so these are some options for us effectively geoengineering. So they're taking the planet and fiddling with it deliberately to make it a safer place to live. Okay, and some of these involve stopping solar radiation coming in, so things like giant space mirrors, which is a little bit far-fetched. But that will cool the planet down, and that would be good, that would help us with our climate change problem. But some of these technologies are also aimed at taking atmospheric CO2 with either artificial trees that suck CO2 out of the atmosphere, or in fact real trees, which are much easier to make. Okay, and they will take carbon from the atmosphere, and then we have to do something with that carbon. So we can bury it in the ground, we can perhaps do something with rocks, we can weather rocks, that actually helps bring CO2 out of the atmosphere. We can try and manipulate the ocean, and that might help us put carbon dioxide into the deep ocean, so it won't be in the atmosphere. So all of these things have massive risks associated with them in terms of the ecosystems that in these environments, but also making sure that CO2 is in the ground. So these are huge problems that make it actually a really exciting time to be an Earth scientist. Kind of related to this idea of sucking CO2 out of the atmosphere and putting it in the ground, there's this idea of energy storage, which is something that we're working on, people in Edinburgh are working on quite a lot, is that if we want to have nice renewable energies, and you might be able to see some wind turbines up in the top corner of this diagram here, renewable energies like wind turbines is great, but quite often it's really intermittent. So the wind blows, and then it doesn't blow, but you need electricity all the time. So one of the solutions that we're looking at is to use the energy when we're producing more than we need to pump air into old oil and gas reservoirs. Okay? So we basically just push air into the ground, okay, and compress air into the ground. So it's a little bit like fracking, which you might have heard of, except we're not trying to break the rock apart, we're just trying to store compressed air in the ground. And then when the wind stops blowing, we let that air back out of the ground, okay, and that compressed air can power a turbine, and we can get some of that energy back. Okay, so this is a geological kind of solution to a renewable energy kind of problem. Okay, and this has all kinds of problems with it in terms of, you know, how much of this stuff leaks out, does it affect the groundwater, that make it an interesting kind of earth sciences problem to solve. Okay, so it's also all of our activities as humans kind of have caused bad things to happen to the environment. So this is some acid mine drainage. So we like things out of mines. They give us kind of metals and things that we can make products out of. But there's an environmental damage to doing that. Okay. So one of the things that some earth scientists do is look at these kind of systems and try and figure out ways of making them better or controlling the pollution in a better way. This image over here is one of the scariest images that I've ever seen. Okay, so this is one of the high-level radioactive waste storage sites from Sellafield. It's where we store some of the radioactive fuel rods from the first generation of civilian and military reactors in the UK. And it's kind of open to the air. In fact, you can see here there's a seagull swimming in it, and there's some kind of like mossy stuff growing on the side of it. This is not a terribly safe way of storing radioactive waste, okay? At all, for a whole bunch of reasons. It's very susceptible to terrorist attack. I mean, if the sides of these concrete tanks fail, the fuel will be exposed to air and it will catch fire, and we will, because it will spontaneously combust with the atmosphere, and we'll get a huge plume of radioactive kind of nasty clouds over most of Europe, which will be bad, right? So this is a stupid thing to do, but we've done it anyway. But the solution to this problem is to store this stuff underground somewhere, okay? Which is a geological problem. Okay, so this is another area which is being heavily researched in this department, but it brings up a whole bunch of interesting questions about the properties of rocks at depth in the earth, how fluids move through them, how those contaminants might migrate out of our storage site over thousands of years of how long we have to keep it there. Okay, so this is a problem that we have, and us as earth scientists will endeavour to solve it for you. So, you're welcome. Okay, so just to summarise what is earth sciences. So, I see it as really having three main components. So we really want to understand stuff about how the earth works. Okay, so why are there mountains? Why are there mountains where they are and not elsewhere? Things like that. It's about natural hazards as well. So some of the processes that cause the earth to be what it is are inherently hazardous to large human populations. So things like understanding how volcanoes work, understanding how hazardous different earthquakes and tsunamis might be, understanding the hazards associated with climate change. These are big topics. And then there's this third kind of like third, I guess, which is resources and energy. So basically getting stuff out of the ground for humans to exist as an advanced civilization. Okay, so that's the stuff we need, but we also kind of tend to make a mess of it when we do this resources and energy. So a certain aspect of earth sciences is really cleaning that mess up. Okay, so these are our challenges over the next kind of century, and these are really kind of earth scientists, geologists, environmental geoscientists, physical geographers that really are kind of really key to solving some of these problems. Okay, so when you guys decide that you want to come to university at Edinburgh or other universities are available, the kind of things that you'll be doing as an earth science degree will be very similar to any other science degree. So you'll have lectures, where you'll sit in a lecture theatre much like this, and have a bearded old white guy speaking to you, and you'll be furiously taking notes. You'll do practicals, which will involve actually looking at like samples, or doing some chemistry in the lab, or taking some physical data and doing some processing with that data. So we've got tsunami data up in the middle there, a topographic map of the Himalayas. But in earth sciences, we tend to also do quite a lot of observational work. So we look at samples of rocks under maybe the microscope. But a large part of earth science's teaching is in the field. So we actually go outside where the earth is effectively performing natural experiments for us, and we go out and we make those observations there. This is what we're going to do some of this tomorrow. This is an example of one of our trips from the Lake District. You'll find that most earth scientists walk around like this because they only look at the rocks. And geographers look around like this because they're only interested in the landscape. We'll try and do a little bit of both tomorrow. Okay, so what I want to talk about now is introduce basically a little mini lecture on plate tectonics. So some of you, has anybody heard of plate tectonics? Okay, it's hard to guess what's in it. I guess some of the university students at the back are like, what? Okay, right. So you've all heard of it, hopefully. So this is this idea that the plates that make up the Earth's crust have moved around from their current positions in the past. And there's quite a bit of evidence for that. So if you look at the coastlines, or in fact if you look at the continental margin edges of some of the continents, they kind of fit together. Okay, where they've been subsequently moved apart. So Africa and South America seem to fit together quite nicely. And then once you've fitted them back together, okay, then you can see that actually the ranges of fossil organisms seem to line up across continental boundaries. And also when you look at the rocks that are formed on those continents, okay, they don't necessarily seem to match the environments they're currently in. So for example, deserts tend to form in these kind of mid-latitude environments where it's kind of hot and dry. And if you go to the Lake District, you'll find the Penrith sandstone, which is basically a deposit that was formed in a desert. But if you ever go to the Lake District, it is definitely not a desert now. Okay, so you can see that there's this geological evidence that the continents were not in the same position that they are now in the past. We can go a little bit further than that. So these are some models of the Earth's magnetic field inside the outer core. So this is this layer of molten iron and nickel and another light element that's kind of swirling around in the centre of the Earth, and that moving metal causes there to be a magnetic field. Okay, and this is the magnetic field with so the North Pole is a south magnetic pole, okay, because north magnets point towards it. So the blue is a north, and that's pointing up. But sometimes, every now and then, this kind of complex geomagnetic dynamo kind of goes a bit crazy, and it breaks down, and then sometimes it flips back to where it was originally, but then sometimes it flips back the other way. So this time we've got south facing down towards the South Pole, which is the wrong way up, and north facing up towards the North Pole. Okay, so sometimes the Earth magnetic field just basically flips up one way and the other. And the other thing about the Earth's magnetic field is it's not just kind of north and south, but there's also a component. So imagine this is the south pole of the magnet, so that's kind of like effectively the north pole of the Earth. At the North Pole, the lines of magnetic force go straight down into the Earth. Okay? And as you move around towards the equator, the lines of magnetic field are actually parallel with the Earth. So when you have a compass, okay, it doesn't just point north-south, okay, but you could also make a compass that actually points up and down. Okay? And the amount up and down, okay, can tell you where you are on the Earth. Okay, so if you have a compass that's kind of pointing horizontally, that tells you you're somewhere near the equator, whereas if you've got a compass needle that's pointing down, okay, that tells you you're somewhere near the poles. So we can use this. So we can find some rocks that have magnetic minerals in them. So this is a lump of magnetite, which is an iron oxide, which is magnetic. And you can see that that's attracted some iron filings to it. So there are some minerals which are magnetic. Okay? And it turns out that those minerals are actually quite common, but in very small amounts in many, many kinds of rock. So if we find these rocks that were formed in the past, all those little magnets in the rock will be lined up with the magnetic field at the time that rock formed. Okay? So we could use that to try and reconstruct, for example, where the Earth's magnetic pole was. And that will help us figure out where the continents were. But also, this is a map of a mid-ocean ridge, and we'll see another one in the next slide, where it's just coloured black and white for which way up the field is pointing. Okay? And you can kind of see that along the axis of the ridge, you've got a black stripe, and then there's two white stripes, and then two black stripes, and it's kind of symmetrical. Okay? And it's symmetrical. Okay, so this is the same kind of thing. This is the Atlantic Ocean, so the UK for now is kind of up there, Europe now I guess is there, Africa and Canada's over there. And along the mid-Atlantic ridge down here, instead of, so this is a map of magnetic intensity, so the strength of the field rather than the direction. But you can see that it's kind of symmetrical pattern about the central axis. And this tells us that rocks are being formed along the central axis, and then being split apart and moved to the side. So you basically get a symmetrical pattern of rocks forming. Okay, and that knowledge has allowed us to work out essentially how old each bit of the ocean crust is. You can see the young crust is by the centre of the ridge, which was formed recently. It gets pushed aside, okay, and then that rock gets older as more rock is formed in the middle. Okay, so this tells us that this is some evidence for mid-ocean ridge spreading, which is a key part of the theory of plate tectonics. Okay, and we can use this knowledge to kind of split up the ocean into these kind of discrete plates. Okay, so we have stuff being formed on the margin of the plate, and then there's nothing really happening in the middle of the plate, no fresh rocks being formed, and then on other margins we have destructive boundaries where plates are coming together rather than being formed and pushed apart. Okay, so we can basically divide up the types of edges of plates into three classes. Ones where nothing really happens, they move side by side. Ones where they're moving apart. So if you move one plate apart, that creates a gap in the middle from which fresh material from below can rise up and start to form new rock at the ridge axis. So that's constructive. or divergent plate boundary, and then you have these destructive or convergent plate boundaries where two plates meet each other and then something happens. Okay, so we're going to have a look quickly at these divergent case. So I just thought this is a place to bring in the place where we use a little bit of physics to explain what's going on. Okay, so this is what we're going to be looking at. This example here. This is a divergent plate boundary. So the plates are moving apart, and that's creating basically a gap, and stuff can rise up into that gap. And this we can then use physics to understand why we would get new rocks formed there. Okay, so the thing is to look at these graphs at the top. So we've got depth down into the earth, okay, and then we've got temperature increasing to the right here. So at the surface of the earth, it's quite cold. In fact, at the bottom of the ocean, it'll be about 2 degrees Celsius, maybe. So we'll be here, and we'll be at the top, okay? Now, as you go down into the earth, okay, because the centre of the earth is very hot, it gets hotter and hotter and hotter as you go down. Okay, and that's what this red line is here. So this is basically just it's called the geotherm. So basically this is how it gets hotter as you go down into the earth. Now the green line on here is the temperature at which rocks melt. Okay, so at the surface of the earth, you have to heat up a rock to 1100 degrees Celsius for it to melt. Okay, but as you go down into the earth, the pressure increases. Okay, you should know that as things go from solid to liquid, they usually increase in volume. So if the pressure increases, it's harder to do that increase in volume. So at higher pressures, you need to raise the temperature more to melt something. So that's what this green line is here. So you can see the green line at depth, we maybe have to get up to 1800 degrees Celsius to melt something. And you can see under normal conditions, it never gets hot enough to melt any rock. Okay? Which is why most of the Earth is solid, which is quite nice. But if we took some of this material here that was at depth and was hot, and we brought it to the surface, okay? If we brought it to the surface quickly enough, it wouldn't have time to cool down, okay? So it would keep the temperature that it had at depth, okay, which would mean that it would cross over this line here, which means you would get some melting, you get some magmas formed, and then those magmas eventually reach the surface and then cool into a rock. Okay? So that's one reason why we get rocks at those environments. The other kind of place we get kind of fresh rocks formed is at basically convergent margins. We get two plates coming together, and we tend to get some kind of volcanoes there. So these are places like Sumatra, Japan, South America, lots of explosive volcanism there. And this is, that's the divergent once again. So, divergent, okay. So this is, just to go back to the spreading argument. So this is some research that's done in this department here, where we're looking at basically this bit of continental crust here in Eastern Africa, where this bit of continent is moving away from this bit of continent, basically forming an enormous crack along the Rift Valley. And this is a fresh crack that opened up a couple of years ago, with some people to scale. And this moving apart of the continental crust is causing lots of fresh rock to be formed in that valley there. So this is basically a new ocean basin that's opening up and forming. Okay, so I'll ignore that one. Okay, right. So these are these subduction zone volcanoes. So this is another reason why we might get melting of rock to form magma to give us volcanoes, which will give us new crust. So rather than stuff just rising up and taking hot stuff from deep, bringing it up shallow so it melts, something else is happening here. Okay? And if we look at our diagram of here, actually what's happening is we're taking material, the ocean crust here, which has been near the surface for a long time, so it's quite cold, and we're bringing it down to a place of the Earth where it's quite hot. Now, because this is cold, it's not going to melt. Okay? So the reason we get melt here is actually because there's something in the crust here that comes out into the rock that overlies the subducting crust. that causes it to melt. And that thing is water. So in a very similar way to if you put salt on ice, it helps it melt. Yeah? So if you add water to rock, it makes it easier to melt. It's kind of a weird analogy, but it's actually true. Okay? So in this case, rather than change the geotherm, rather than change the white line, the red line, rather than change the red line, we're actually altering the properties of the rock by taking water from the ocean, putting it into this oceanic crust, subducting it down, and as it comes down to this high pressure region, the water gets squeezed out of the rock essentially and goes into the overlying mantle here, and that causes the properties of that rock to change such that it's easier to melt. And that causes us to get different kinds of rock formed under that volcano. Okay, so that's what happens. So basically, this slab almost never melts in an island arc. It's the overlying mantle that actually melts because we're adding water to it. Right. Actually, I'm going to skip over that, and so there is basically another kind of continental boundary where continents hit each other, and you get a much different kind of collision zone. It's basically this guy here, the Himalayas. So the theory of plate tectonics, as I've kind of rushed through it, is that we basically have these plates, okay, that are effectively quite rigid. They don't change much through time, okay? But at the edges of those plates, we have a lot of deformation happening. So we have volcanoes, we have new rock being formed. So this is a map of earthquakes. So you can see the earthquakes are concentrated along the edges of these plates, okay? So I guess the theory of plate tectonics is that you have rigid plates that exist for quite a long time through geological history, but over the margins of those plates you have a lot of deformation. So what I'm going to do now is talk about a little bit of research that I did with a student when I was at another institution. So we were looking at this region of Mongolia. Okay, so we have basically a plate boundary down here where India is being pushed up into basically Tibet, and this is basically causing Tibet to be a big high mountain range. And we were actually looking up here in this mountain range up here. It's a bit odd that that mountain range exists. So this is the Altai, the Gobi Altai mountain, I think, and the Tian Shan, which is these mountains down here. So these mountain ranges, why does that mountain range exist? It's nowhere near a plate boundary. Okay, so what we wanted to know was, what are the actual rates of deformation that are going on up in that mountain range up there? Is this a relic of some previous plate boundary, or is this actively deforming? So what we did, Laura went to Mongolia. I didn't go to Mongolia because it's a really long way away, and they still had the bubonic plague, so I decided not to go. Anyway, so we went. Laura went, and you can see that maybe you might make out there are some faults, some black lines marked on this map here. You can kind of see this is one of them here. It's called the Olgai fault, and this is a satellite image of that. You can kind of see that as you go through this area, there's a kind of a line in the sand, basically. And this is where the fault, where the two bits of rock are rubbing against each other, it's outcropping in the environment. So that fault actually runs through up here, okay, through up here, and basically she went out in the field, made lots of observations and kind of mapped out where that fault was. And the neat thing is that this fault is being cut across by an alluvial fan. Are you happy with what an alluvial fan is? So, yeah. Yeah, so basically it's a deserty kind of environment, and there are occasionally flash floods, and those floods bring lots and lots of sediment out of the mountains and then just dump it in basically a nice fan-shaped deposit of bouldery gravel. Okay? So this has come down and covered up this fault, and then on top of that fan there have been some streams that have cut down, and then what's happened is then after that's happened, the fault has carried on moving. So you can see that this stream is then offset, and the stream is offset where this fault is. So what we're going to do is we're going to measure So we used a GPS survey, so we measured how the topography of the land. We mapped out where the streams were. We measured the distance that stream was offset. Okay, that tells us how much deformation has happened. But if we want to know the rate, okay, we need to know the time it's taken for that deformation to happen. And the way we've done that is we're using a technique called cosmogenic exposure dating. So basically, we want to know how long that surface that's been deformed has been exposed to the atmosphere. So the way we do that is using cosmic rays. So cosmic rays are formed by large supernova stars exploding long way off, basically billions of years ago and billions of light years away. But these produce hugely energetic cosmic rays. And when these hit the atmosphere, they hit particles in the atmosphere and produce this huge shower of secondary particles. So electrons, positrons, neutrinos, other isotopes of the elements that they've hit, all kinds of crazy elements get formed. So this happens in the atmosphere, but sometimes cosmic rays make it down into minerals at the Earth's surface. Okay? And that changes the chemical composition of those minerals into isotopes that otherwise would not exist. Okay? Things like beryllium-10, which doesn't exist naturally, although this is a natural process. So what we do is we measure, so the longer a mineral has been exposed at the surface, the more of these kind of crazy isotopes that it accumulates. So if we measure the concentration of those, and we're typically measuring almost individual atoms per gram of material. I didn't put that picture in. Okay, using hugely massive mass spectrometers. That gives us an age of how long that surface has been exposed. So this is what we do. We basically combine our fault offset, okay, with a surface age, okay, and this gives us a rate of movement on that fault. Okay, so I mean, I could ask you to work out how fast it's moving, but it's kind of one number divided by the other. So it's somewhere between 0.4 and 1.2 millimeters per year. Okay, that doesn't seem like a huge amount. That's quite unlike. It's very slow as far as we're concerned, but as far as the Earth is concerned, it's actually reasonably fast. So if we're looking at these figures here, so these are rates of plates moving apart in centimeters per year. So our 0.4 might be 1 millimeters per year. We may be a factor of 10, maybe a factor of 50 slower than these proper plate boundaries. Okay? Okay, but bear in mind, so up there we have we've measured the rate of movement on one fault to be maybe 1 millimeter per year, whereas out on some of these boundaries here we may be 50 millimeters per year. But actually there are lots of faults in the Gobi Altai Mountains. So if you add them all up, we're maybe only 10 times less than a proper plate boundary. But we still are. We're up here, so we're not in the middle of a plate. So this kind of does put a bit of a hole in the theory of plate tectonics, in that actually deformation is not limited to the edges of plates. There is deformation going on in the middle of the plates. Okay, so there's something that's transmitting stresses through from the plate boundary thousands of kilometers away into the center of the plate. So that's a bit of a problem that as Earth scientists we have to think about and worry about. Okay, so I'm not going to go on and discuss that any further because essentially we don't really know all of the answers. So this is what kind of makes it a new exciting science, because there are still answers out there to be got. Just quickly, I'm going to whiz through things about geological time. So one of the really interesting things about Earth sciences is the Earth is really, really old, and there are processes that are important for understanding how the Earth works. So building of mountains, the evolution of life, that can only really be addressed by looking into this record that we get from rocks that is this enormous amount of time long. So this is basically a time scale. So we are here in the Holocene, so this is 0 years ago, Back here is the basically the formation of the Earth, which is about 4 billion years ago, so 4 times 10 to the 9 years ago. The history of life kind of really starts kicking off up here about 1 billion years ago, and then when we start getting proper fossils that we can kind of identify, about 550, 540 million years ago. And why does that matter? So basically, we can build up those age scales using just layers of rock. One layer, the layer below it has to be older because the layer on top was then formed on top of it. And we can look within these layers at a whole bunch of different fossils, and we can see that those fossils are characteristic for each layer in the rock, essentially. So we can put all of our history of evolution into a relative time frame in terms of this must be older than this, which must be older than this. We can start to put absolute ages on some of these things to work out rates of change of evolution using some of the radiometric dates that are kind of brought from the cosmogenic isotopes, but we use slightly different chemistry. So I'm going to skip over because they're quite boring and talk about dinosaurs. So some of the research that we do in the department here is about the evolution of dinosaurs and mammals. Okay, so this is I can't remember the name of it. This is one, I think it's called Pinocchiosaurus or something. So we're discovering new dinosaurs all the time, discovering new things about these dinosaurs. So for instance, you can maybe make out that some of these things were feathered. But it's not. We're not just interested in finding a new thing and going and oh, this is a nice shiny new thing. We're actually interested in how these things evolved. Okay, how one group of organisms changed through time and split into two separate populations, and what was it that actually drove those processes? Okay, so what is it that's causing life to evolve in these different ways? So is it environmental change? Okay, so in this case we would compare the records of different fossils to the environmental conditions preserved into the rocks. Did the environment change and then the fossils change, or is there some inherent process to evolution that causes kind of species to evolve through time independent of environmental forcing? Okay, so some pretty dinosaurs there. Yeah, so one nice example is the evolution of birds. Birds evolved from these kind of theropods, which were kind of like a velociraptor here, which is kind of like a chicken-sized dinosaur. And there are a number of characteristics which appear to essentially be pre-adapted for the existence of birds. So the hollow bones, the large breastbone for flight, these things seem to have very little role in these organisms, but then later on they start to become more important. So understanding the timing relationships between the changes in the fossil record and the changes in the environmental record are quite important. Okay, so these are some of these nice dinosaurs. Okay, right. So okay, so that's kind of the lecture kind of finished with for now. So tomorrow we are going to go into the field. So we're going to go and see our own Edinburgh's volcano, which is Arthur's Seat, which is up here, and we're going to see some other rocks over here on Salisbury Crag. So you might have seen these out the back of Pollock Halls. You guys staying in Pollock Halls, yeah? Okay. So we're going to go and have a look at these. So just, I guess, a little bit of health and safety first. Okay. So this year, somebody died on that hill. Okay. They died on that hill because they fell off it. Okay. So we need to make sure that you are prepared, not for death, but prepared to go into the field. So tomorrow it is likely to rain. Okay, so you will need to have something warm to wear and something waterproof to wear. Does anybody not have anything waterproof to wear? One person, 2 people, 3 people. Are you not sure? Have you been in the rain before? Okay, so I will try and bring an extra coat or 2, but just in case, be prepared for slight wetness. it will also potentially be slippy underfoot. Okay, so does everybody have sensible shoes? These are sensible shoes. Well, these aren't sensible shoes because they've got metal at the bottom, but kind of walking shoes, no flip-flops, high heels, not such a good idea. Okay? So wear something warm, wear something sensible. We'll only be out for, I think, an hour and a half. That's all I've been given. So what we're going to do, I'll show you a little map of that. So what we're going to do, so basically, Scotland, this is Scotland, and you might be able to kind of just make out from just kind of like an overall kind of view that Scotland's basically, the geology of Scotland is made up of a series of stripes. Okay, so at the top we've got like a pink stripe that kind of comes down here. Then we've got a kind of a pink and brown stripe, a blue stripe, a yellow stripe, and we've got a red and I guess teal, grey-green stripe down there. Okay, so all these different stripes are basically bits of crust that have been formed at the margins of a continent. Okay, so a bit of you've had a continent and you have something that's kind of smacked up against it. Okay, and that's left a stripe of rocks if they've formed, and then another bit of continent has come up and smacked up against it. So over geological history, maybe I guess the oldest rocks in Scotland are kind of up here. These are about 2.5 billion years old. Then the brownie layer is here. That's about 600-700 million years old. And then we basically get slightly younger as we move south. So these different layers of rock have been smacked up against the side of Scotland. And as this has happened, we've basically had a whole bunch of tectonic activity. And some of that we're going to see is one of the volcanoes that formed actually as some of this stuff was collapsing back apart. Okay, so if you form a mountain range, you push up all of the crust into one big kind of mountainy lump, and then if you stop pushing at the sides, it starts to collapse back down again. Okay, as it collapses back down again, you start pulling apart the crust. And when you pull apart the crust, hopefully you might remember from earlier, you start bringing material up into that gap that you're pulling apart, and that causes volcanoes. So we'll see one of those volcanoes tomorrow. So what we're going to do is, so this is kind of rubbishy Google Earth images of pollock halls. So these are pollock halls. The main entrance reception is this building here. Yeah. So at 9:30 tomorrow, I will be at this roundabout. As so will you. Okay. So you need to have everything you need to be outside for an hour and a half, and you need to exit here and walk around to here. There might be a sneaky back entrance. Does anybody know where the sneaky back? No. Okay. So go out the main door and to that roundabout. Okay, right, that I think is us done. So we're going to do some practical time now. So I did hand out these post-it notes at the beginning, and I had meant to say, if you have questions about the talk, write them down on the post-it notes, and then forgot to say it. So if you have any questions about anything, about geology, about stripy jumpers, about anything, write them down. Or just ask them, that's fine. Then you can hand them in and I'll try and answer them now or some other day, okay? So feel free to do that. If we could, I guess, split you into 4 groups. So you 4 could be a group. Show up, be a group. You 4, be a group. And then you 4, be a group. And then a group of 3. Which is good, right? You can be a group of 3. So if you could do that, and then if you could kind of come round to the front. So if one group could be over these rocks over there, what we're going to do is up. Okay. So you group from here, you group from here, you group from here.